Exercise 32 show that in abelian category, any morphism C2D small f could be written as a composition of a monic with an epimorphic. So basically, wow, this is more or less proving the fact coimage of f is isomorphic to image of f, where coimage f by definition is defined to be the co-kernel of kernel of f, while image of f is defined to be kernel of co-kernel of f. So it depends on how you define your abelian category. If you require your abelian category to have kernel and co-kernels, and then you could just add the last axiom to be co-image isomorphic to image. If you define your abelian category to using axioms like what Grothendieck did or Rival did, that means pre-additive and then additive and then have kernel and co-kernel, and finally requiring that is normal, means any monic is a kernel of some co-kernel, or is a kernel of its co-kernel, and any epimorphic is the co-kernel of its kernel. Then in that case, you have to prove as exercise this is true under your definition of abelian category. In your definition of abelian category, this is always true. So this exercise is more or less like proving this, but seems later I'm asking you to prove something weaker, which means put co-image of f there and to show that there is an injection. So if you have this isomorphism, then you have this injection. Basically, this is just by definition you have co-image of f, and you have a monic image of f, because we have proved any kernel is monic and any epimorphic is any co-kernel is epimorphic. That's actually true in any category, because equalizer is always monic and co-equalizer is always epimorphic. And so by the universal property we got this map, and if you know its isomorphism, then what is proved to be injective here is just computation of this isomorphism with that injective. Okay. Conversely, if you could prove this is isomorph, this is morphism, can you further prove this is actually showing that co-image of f is isomorphic to the kernel of the co-kernel of f? Maybe just use universal property to, firstly, the composition is 0 is obvious. Secondly, can you show it satisfies the universal property? Okay, to think about the relation of this, isomorphism and the fact there exists the monic. What is the relation? Let's first prove that for any morphism small f, we can rewrite it into composition of epi with monic with epimorphic. So this proof is rather complicated. So there is always morphism, firstly, from this coimage of f to D. This comes from the universal property of coimage. Because f composes kernel f is 0, so there exists unique morphism J such that this diagram commutes. And we want to show that this J is harmonic. So basically, if we could prove that this J is harmonic, we are proving that because this is J. The unique morphism is the unique morphism with the composition. So if we prove J is harmonic, then we prove this is harmonic. Hopefully you could compute or prove kind of duality of this exercise by showing that if you first start with a major f and then prove that there exists some epimorphism, in that case what you're doing actually is you construct this, I call it G prime U, to show this G prime is epimorphism. This all forces to show that this is epimorphism. And so this is both epimorphism and isomorphism, and so it is epimorphism and harmonic. In the abelian category, this tells it is isomorphic because abelian category is a balanced category. And this solves this exercise I put here. Okay, so which means this exercise is equivalent or as corollary show that in abelian category coimage of f isomorphic to image of f. Okay, so let's prove this J is harmonic. What we want to do is by definition we want to show that if J composed with some test morphism, let's call it small t, equals 0, then this test morphism is 0. This implies this is harmonic, right? Because this is abelian category, in particular pre-additive, so there's 0 element in every homomorphism. If there's 0 element, then GF equals GF2 implies F1 equals F2. This is an equivalent to G composed with some F1 minus F2 equals 0 implies F1 minus F2 equals 0. Basically, this is some theta. This tells that G composed with morphism is 0 and implies the kernel of G is 0. It implies this is kind of saying kernel of G is 0, so it's harmonic. Okay. So in the following we are going to prove this J is harmonic. That's what we are going to prove in the following. Okay. So the first step, I say step 1. Let's first consider what is co-kernel of this test morphism. And so we construct this co-kernel denoted by co-kernel of T. And then because by the universal property of co-kernel, because this test composed with G is 0, so by universal property of co-kernel, this G factorized through co-kernel map. So there exists some, let's call it Y, make the diagram commutes here. And notice that the composition of C to co-kernel of kernel F, so this vertical one, with this one is again epimorphism, because both epimorphism, and then any epimorphism is co-kernel of some map. So in particular, this is co-kernel of some map. Let's call this H. I think this is very technical, very important part of this is we're we are showing the equivalence of a different axiom. First axiom is this, or as I said, alternative axiom is saying that any epimorphism is co-kernel. Here we are using that. This is epimorphism, so it is a co-kernel. I think this is crucial. Key use, essential to. This is where we use abelian category. Okay, and then notice that F composed with H. F composed with H. Is the same as J composed co-kernels and composed with H. And then J is furthermore Y composed with co-kernel of T. And so finally, this is the composition of this, this, and this, but this is 0. And so this is telling that using the universal property of a kernel, there should be morphism from H to kernel. So there exists some, let's call it small l, from H to this kernel. We rewrite. Here is the kernel of F. Then add the universal property. There exists a unique morphism small l such that this commutes. And then we now consider co-kernel of kernel F composed with that small h. Consider so here and here. Using L, this gives you the composition of this 3, but then this is again 0 because kernel and its co-kernel composition is 0. And so this time it is telling that H composed this is 0, and using the universal property of a co-kernel of H, which is this one, so this composition is a co-kernel of H altogether. The universal property of co-kernel of H said that co-kernel of H would factorize. So this morphism would factorize through co-kernel of H, which means there exists some morphism. Let's call it small m, such that diagram commutes. That is saying M composed with co-kernel of H equals co-kernel of kernel F. And then notice that we could also rewrite M composes co-kernel of H. Because the co-kernel of H, by our construction, is co-kernel of T and the co-kernel of kernel F. Then rewrite it. It becomes M composes co-kernel of T. Composed with co-kernel kernel F. But then by the identity here, we know that M composes co-kernel of H equals co-kernel F. So we got this identity here, plus the fact co-kernel is epimorphism. This is telling that M composed with co-kernel of T is identity. And this is saying that co-kernel of T is split. And this showing that this is actually not only epimorphism, but also monomorphism, morphism. The reason is, for example, you could say it here. So this existence of this left inverse of M is showing that this co-kernel is kind of like injective, but here we mean more morphic, because for whatever test morphism alpha, applying this M composed with this M, and you will see that that test morphism alpha is 0, so this co-kernel X is morphic, and so it is epimorphic and hence isomorphism. And if the co-kernel of T is isomorphism, this will tell you that this T is 0. Because we want to prove this test morphism T is 0. And finally we reduce it to the fact that this T, this morphism, we want to prove it is. So let's summarize the very general case. We got to prove that, we want to show this is 0. What we do is we take the co-kernel of it. And then finally we show that this is actually an isomorphism. Which means both epimorphic and morphic. Any epimorphic is co-kernel of its kernel, and so this is saying that this is the co-kernel of its kernel, but it is co-kernel of this. It should say that this is the kernel. If we know this is morphic, then this is the kernel of its co-kernel. But at the same time, it is morphic is also saying that its kernel is 0. And so saying that this is 0. So what I'm not quite sure is that when I'm saying that it is the co-kernel of its kernel, and it is also the co-kernel of T, kernel of it, can this show that T is the kernel of it? If that is okay, then this is okay. And finally, so we have proved that J is morphic. That's what we want to prove.